Okay. Next, we're moving on to Gibbs free energy. And you see how this is a big like energy storm or whatever. And that's essentially what Gibbs free energy is it's the available energy that can do work from a reaction, okay? So if you have a chemical reaction, what Gibbs free energy measures is essentially when you use that reaction, how much energy does that reaction produce that can actually be used to do something? Again, make an engine work, fridge work, motor, anything like that. Okay. Okay. So Gibbs free energy, right? How do we determine, just ignoring that, how do we determine whether or not a reaction is favorable or not as a whole? I've mentioned whether it or not a reaction could be favorable in terms of entropy. Again, if it goes from a solid to a liquid, it's favorable. If it goes from a liquid to a solid, not favorable. And if it goes from a high enthalpy to, if there's a negative change in enthalpy, like it's exothermic, it's favorable. If there's a positive change in enthalpy, it's endothermic, it's not favorable thermodynamically. But what if it's conflicting? What if it's entropically favored, but in enthalpy it's not favored, right? How would we know that? Well, we use this quantity delta G to determine that, and delta G is the change in Gibbs free energy. Delta G is a measurement of a reaction to determine if the reaction is favorable overall, taking into account all factors as I mentioned. Some reactions have positive delta S, which is favorable, but a positive delta H, which is not favorable. So it's hard to tell whether or not the reaction as a whole is favorable without using delta G. And this may be a small point of confusion. So in terms of favorability, delta S, entropy, is favorable when it's positive and non-favorable when it's negative. Delta H is the opposite. It's favorable when it's negative, not favorable when it's positive. Try not to remember it based on the signs. Try and remember what it is, favorable or not favorable, based on what actually is happening. Just try to understand it. For example, what does a positive delta S mean? Well, it means you have more entropy at the end. You have more entropy at the end than you started with. Entropy, you know, is what the universe wants. It wants randomness. So if you have a positive delta S, that means there's more randomness at the end than there is randomness at the beginning, which is good, right? That's what the universe wants. So you would want a positive number in order to be favorable. Whereas a negative number for delta H would mean that the reaction is exothermic. Well, if a reaction is exothermic, then it's releasing energy, and that's what's favorable. Negative means exothermic, and exothermic is favorable. Positive is endothermic, which is not very favorable. If you want to think about it again, start and finish. In delta H, if the ending energy is higher than the starting energy, that means that energy must have come from somewhere. So what that means is it came from somewhere else, and it had to have been absorbed. That's not good. We don't really want to absorb energy from other places because that means you're taking energy away from something else. We don't really want that. We want to be releasing energy. So we want the energy of the system to be lower at the end than it was at the beginning. Okay. How do we find delta G from delta H and delta S, right? So we have this formula, delta G equals delta H minus T delta S. And T is temperature in Kelvin, okay? The temperature of reaction. This only really works at constant temperature if a reaction is at constant temperature, but on the MCAT, almost all reactions will be at constant temperature. If the delta G is negative, the reaction is exergonic and favorable. If delta G is positive, the reaction is endergonic and unfavorable. This may seem familiar. This is the same system we used in delta H. Delta H also, if it was negative, it was exothermic, and if it was positive, it was endothermic, and it was favorable and unfavorable respectively. Delta G works in the same way. Exergonic means you're releasing. Gonic is just a word that they use to describe free energy, right? So Gibbs free energy. You don't have to like go that deep into it, but again, exergonic, exo, outside, releasing it outside, endo, inside, taking it in. Looking at the simple math, even in using just this formula and what we know without even knowing anything about like delta G or anything like that, we can see that if delta H is a negative number, meaning that it's favorable, delta H is favorable when it's negative, and delta S is positive, which also means it's favorable, right? I'm going to draw it on here. So we have a negative number minus, temperature is always a positive number. Temperature can't be negative, especially in Kelvin, at least. In Celsius, it could be, but in Kelvin, it could never be negative. We take temperature and we multiply it by a positive number. So we take two positive numbers and we multiply them together to get a positive number. A negative number minus a positive number, that's always going to be a negative number. No matter what the numbers are, it's always going to equal a negative number. And we know that when delta G is a negative number, it's also favorable. So if delta H and delta S both favorable, delta G is also always favorable under any conditions, right? If we look at it differently, delta H is positive, so it's not favorable, minus T is always positive, delta H is negative, which means it's also unfavorable. Positive number times a negative number is a negative number. When you do double negative minus a negative number, it's actually two positive numbers, so it's a positive number plus a positive number. Well, that's always going to give you a positive number, no matter what the conditions are, no matter what the numbers are. It's always going to be delta G is always going to be positive, which is unfavorable. The problem comes in what if delta H is positive minus, and we say T is also S is also positive. T we know is positive, so it's a positive number minus a positive number. Well, that depends. So those 5 minus 3, it would still be positive. Those 5 minus 10, it will be negative. So the rule in this case is that if they're conflicting, if the delta H and the delta S are conflicting in whether or not they're favorable, the rule is if temperature is very high, that means delta S wins. It will choose, delta S is what determines whether or not the reaction as a whole will be favorable. If temperature is low, delta H is what wins, or it will be what determines whether or not the reaction is favorable. And we can see that here. So like so this positive number in this parentheses is made up of T times S. If we know that S is positive and H is negative, right? If T is a huge number, it's like, if we pretend that delta H is like, say 10, right? Minus some two numbers. Let's say S is 5. S is 5. So it really depends on what the T is, right? If the T is a big number, like 5, well, that's 10 minus 25, and the resulting is negative, right? And negative is favorable for delta G, and delta S was what was favorable in this reaction. Delta H was not favorable. It's delta S that was favorable. Because the temperature was high, delta S was favorable. Delta S determined what the favorability of the whole reaction was. If we say that temperature is low, say 1, so pretend it's a low temperature 1, right? 1 times 5 is 5, 10 minus 5 is a positive number. Because temperature was low, delta H is what was the deciding factor, and delta H was not favorable, so the reaction as a whole would be not favorable. Okay, so at high temperatures, you look at delta S for favorability of delta G. For low temperatures, you look at delta H for favorability of delta G. Units for delta G are usually, again, joules per mole, because it's a form of energy. It's energy and it's for a reaction. So again, per molar basis. Okay. Right, and there is a chart for Gibbs free energy. So, there is a chart for Gibbs free energy that we put in the chat. Please look at that, memorize it if you want to, but you can really like think it out, kind of understand it. If you do enough practice now, by the time you get to the MCAT, you'll have that chart. Like you'll be able to do that in 2 seconds. You don't have to memorize anything. Think about it for a little bit and see what you would have chosen if you didn't know the answer. Try and like think it out and see why a certain answer might be the correct answer. Okay. Hopefully everybody's had enough time. I'm gonna see, well, the answer, as I showed before accidentally, it's A, it's exothermic. But I want to go over this and I want to explain like exactly why this is. So what do we know? Well, we know that delta S is negative. We have a negative delta S. Negative enthalpy is negative H as well. I'll actually erase that here. It's a little bit confusing. Right, we know that H is negative, S is negative. What does this tell us about the reactions, right? It's exothermic. We know that H is exothermic because it's negative. And we know that that's favorable, right? That's good. S, however, is negative, which is in terms of entropy is not favorable, right? That means that the energy at the end is less than the energy that the entropy that you started with, which is not good, right? So that's an X. What does this mean for G, right? And endergonic and exergonic refer to G. Well, it means it depends. If the temperature is high, delta G would also be if temperature is high. Here, I'll draw it out. Temperature is big. It's a high temperature. It's an arrow pointing up. You would look at what the S says, right? You would look at the entropy, and the entropy is not favorable. So what that means is delta G would be positive, which is not favorable, right? If instead temperature was low, we would look more at delta H, and delta H is favorable, so delta G would be negative, and it would be favorable, right? I'm not going to draw it all out, but hopefully you understand by now. So what does that mean for this in terms of this question, right? Well, we don't have enough information. We don't know what the temperature is. We don't know the numbers, right? So we don't actually know if it's exergonic or endergonic. We can't figure that out because it could go either way, right? Well, exothermic or endothermic, we can figure that out. We know that it's exothermic because delta H is given to us and it's a negative number. A negative delta H is always exothermic, right? Because it has less enthalpy at the end than what it started with, or less energy at the end than what it started with. What does that mean? Well, that means it had to release some energy to the outside, right? Exo had to release out. Okay, so with that we have A. A little last quick thing about delta G before we move on to a different topic. So there actually is a relationship between delta G standard and KEQ, which is the equilibrium constant. We haven't really covered equilibrium yet, but we will soon. And if you guys already know from previous courses, or we actually covered equilibrium in a different program before, maybe about a month or so ago, or 2 months ago. But if you know what equilibrium constant means, then this may make sense to you. And there's a relationship between this and delta G standard. Delta G standard, which has this like little degree sign on the top, is different from delta G. And we'll cover those differences a little bit later, but just know that they're a little bit different. The formula for delta G standard is negative RT ln K, where NK is KQ, at equilibrium, where R is the gas constant, 8.314 joules per mole Kelvin, right? And again, if you want to actually look at units, which I always highly recommend doing, you know that R is joules per mole Kelvin, temperature is Kelvin. If you multiply R by T, Kelvin in the denominator and Kelvin in the numerator cancel out. And then you're just left, KQ is unitless, it's a unitless number. So it adopts whatever units. It's essentially like a constant like 5. So if you multiply something by 5, the units wouldn't change. And what you're left with for R is joules per mole, which is the units for delta G, right? There's also the formula delta G standard equals negative RT ln Q. When the system is not at equilibrium constant or K can only be at equilibrium, right? That's why it's the equilibrium constant. When it's not equilibrium, use Q instead. It's very similar. It's not extremely important. Just know that if it give you a Q, you're probably using this number, right? A big Q, capital Q. right? You're probably using this equation. That's really the only thing big Q is ever used for, in the MCAT at least. Okay. And like I mentioned, there is a difference between delta G and delta G standard. Delta G standard is the delta G of a certain reaction at standard conditions, STP, standard temperature and pressure. Standard temperature is 25 degrees Celsius or 298 Kelvin. Standard pressure is 1 atmosphere. And I'll have this all on the slide in a bit. Usually in biology, we don't do things at STP because the body is not 25 degrees Celsius, it's 37 degrees Celsius. So we don't use delta G standard in biology. In chemistry, we do because most chemical experiments are done in STP, right? And standard temperature is like room temperature. It's like 25 degrees is what room temperature is. Right, so like I mentioned, delta G depends on temperature. Delta G standard is always at 25 degrees Kelvin, whereas delta G not standard is the delta G at whatever temperature you're looking at. If you're looking at 37 degrees Celsius or I believe it's 313 Kelvin, that would be the delta G would be different than the delta G standard of a certain reaction, right? And again, this will all be on a slide and I'll cover this in a bit. First, I want to go through this question, right? Please take a little bit of time, really think about it. I know this is a really hard one. Takes a bit of time, a little bit of thinking. Highly recommend using pen and paper, right? Let's go over this in a second. Okay. So what do we know? We know what delta G standard is, right? And it's negative 30 kilojoules, right? What expression gives the ratio of ADP to ATP? So what is that, right? That may be throwing some of you off. Well, if you remember what KQ is, okay, I'll try K, right? And it's the concentration of products. Yeah, products. Sorry, it's a little bit hard to write on it. A little bit hard to write on the mouse. But yeah, products over concentration of reactants, right? I'll just leave it as R, but that's concentration of products over reactants, right? What are the products and reactants in this case? Well, the products are ADP and phosphate alone. So there's actually 2 in the numerator, but they told us the concentration of phosphate is 1. So multiplying anything by 1 is just itself. So we can actually just eliminate that, right? So it's just the concentration of products. The concentration of products is just the concentration of ADP. Concentration of reactants, well, water we always get rid of because water doesn't really matter. And if we have it in the reactants or on the product side, we just get rid of it. We don't do it when we're calculating KQ. So essentially what K is just concentration of ADP to ATP. Well, that's what the ratio, right? So what they're asking us to find is actually K. So K is the unknown, right? And they give us RT, which is 2.5. Well, we have an equation that we can use, right? G equals RT ln K. We know that RT is 2.5, so we can actually solve it. We don't need any temperatures, we don't need any R's, we don't need anything. 2.5 times ln K. And we know that this is negative 30. We do negative 30 divided by 2.5. We get 12, right? 2.5. We get 12 equals ln K. And I gave a whole thing when I gave this lecture before on how we would solve this, right? Some of you may not know how to do logs or ln. Well, think of it just like you do multiplication and division. This was 2.5 times ln K. So to get rid of this 2.5, what you had to do was you had to divide both sides by 2.5, right? Division is the opposite of multiplication. If you divide both sides by 2.5, do the opposite operation, you can just get rid of this 2.5 to get to 12. Well, ln K, you want to get rid of the ln. So what would you do? The opposite operation of ln is e to the power of. So what you would do is you do e to the 12th equals e to the ln k, right? So ln k. Well, e and ln are opposite operations, just like multiplication and division are. If you multiply something by 5 and divide it by 5, nothing happens. You can just get rid of both those. Same thing here. Take e to the power of something and ln of that thing, you can just cancel them out, right? And what you're left with is just k equals e to the 12th. And that's how you get the answer, right? Yeah, okay, so yes, I might have misspoken. Yeah, STP is, my bad. STP is 273 degrees Kelvin. Standard conditions, which is actually what we're using. We're not using STP, we're using standard conditions for delta G standard. That's 298, right? Oh, and I'm sorry, I actually negative RTL and K. So that's why the negatives cancel out. It's negative RTL and K. Yes, this is the last question and I'll move on. RTL and K is used to help find Gibbs. Yes, or in actually this case, we used Gibbs to find K. But yeah, it's an equation. What it means conceptually is that the free energy and the equilibrium constant are related. That's what it means conceptually. We already knew that it's related by T. Gibbs free energy depends on T, on temperature. We knew that from the equation we had before. The delta G equals delta H minus T delta S. We knew it was dependent on T. Now we also know that it's proportional to K, to the equilibrium constant. Equilibrium constant and G are related. This is kind of a small link between kinetics and thermodynamics, but we'll really cover that more later.